Simultus Functional Training, Part 7, Coordinate Systems and Kinematic Relationship Tree. In this part of the training, we will show you how to define the kinematic relationships of our device in Simultus, using the example of a multi-axis module with 4 degrees of freedom. We prepared the 3D model in the previous part of the course. We also demonstrated how to download the CAD drawings from manufacturers' websites and convert them to a format that can be imported into Simultus. Before we move on to the next part of the work on the prepared device model, we will say a few words about the coordinate systems. In addition to the fixed main coordinate system discussed earlier, a specific number of user coordinate systems can be inserted into the 3D space. These systems can be placed in any position and can feature any orientation. Let's put such a system into our project. After pressing the Add Axis button, the coordinate system will appear at the 0, 0, 0 position. By selecting it, we will see its properties window on the list. We can give the system a new name, check its ID and change the starting position of the system. We can move it to the one of the 3 axes, X, Y and Z, and change its orientation. The orientation of the system is consistent with Euler's definition of angles. Angles have the following designations: alpha, beta and gamma. Let's set the beginning of the system at a point with 200, 300 and 400 coordinates. It is worth experimenting by adjusting the position and orientation of the system. We'll import different sizes of solids into our project. Sometimes they can obstruct the layout view. That is why we can adjust the length of each axis to our needs. The vector 0, 0, 0 button moves the system to the origin of the coordinate system to which it is attached. By default, the new system is attached to the main coordinate system of the project. The position and orientation of the coordinate system in space are determined by the values from the Properties menu we discussed earlier, and the values set in the function block diagram. For simplicity, let's move our coordinate system in only one x-axis by 100 mm. Let's reset the other coordinates. Now let's insert the 6DOF axis function block from the I/O tab into the diagram. This block has 6 inputs, 3 offsets and 3 orientations. Let's define which coordinate system we want to move, and let's connect a slider to the X input. Let's set the output variation range from -100 to 100. After running the simulation, first in 3D visualization and then on the function block diagram, we can change the position of the slider and observe what is happening with our system. As you can see, the system changes positions in the x-axis. If we set the slider in 0 position, then the system is in its initial position set in the Windows properties. It is shifted in the x-axis by 100 mm. By moving the slider to 100, we move the whole system to 200 mm. The position of the coordinate system is the sum of the values from the property window and the function block, controlling its position. We suggest you to change the position and orientation values yourself and experiment with the coordinate system. We will now connect another slider to the Y input of the function block. We can simultaneously control any coordinate. Orientation inputs of the 6DOF axis block require angle values expressed in radians. We can use function blocks that convert degrees into radians. Let's connect a 3D solid to the coordinate system. By moving the coordinate system, we move this solid. In the control systems that we will build, the position set in the block properties will be the starting position. The position set through the 6DOF axis function block will be the position from the control system. Let's return to our device now. Our device already has a structure. It features 4 degrees of freedom. Therefore, we will define 4 coordinate systems to which we will attach the appropriate mechanical elements of our device. Before we begin to define the kinematic relationships in our model, we will make one correction. In the previous part of this training, the name of the short axis was mistakenly set as 1000, while it should be 500, and the name of the longer axis was set as 500. This axis should be named 1000. Let's change the names so that they do not cause mistakes at later stages of our work. Our device moves in 3 axes: X, Y, and Z. In addition, the slider rotates in the vertical Z axis. To determine kinematics, we will need 4 coordinate systems to which then we connect the moving solids of our device. Let's create these 4 systems and name them accordingly: CS1, CS2, CS3, and CS4. CS as a short from coordinate system. Let's add these systems to the project by using the Add Axis button. We will now introduce kinematic relationships resulting from the design of our device. Let's take a closer look at its kinematic chain for this purpose. Its base is the fixed base of a double module with a stroke of 500 mm. The blocks of this module will move along the green y-axis. So let's add the letter y to the name of the first coordinate system. By the way, it is worth mentioning that the x-axis of all coordinate systems are marked in red, the y-axis are green, and the z-axis are blue. The 500 modules blocks are attached to the body of the next module with a stroke of 1000 mm. Thus, the rest of our device will move in the y-axis, along with the blocks of the 500 module. The block of the 1000 mm module will move along its body in the x-axis. Let's add the letter X to the name of the next coordinate system. This system is kinematically linked to the first system. Therefore, let's connect it to the first system. This can be done by using the drag and drop method. Just grab the second system with a square on its left side and drop it in the area of the system to which it should be connected. From that moment on, as you can see by the structure of the created tree, the CS2X system will move with the CS1Y. This way, we created the first kinematic relationship in our device. All kinematic relationships of our device will be visible in the form of a tree on the left side of the visualization window. The tree can be freely edited, keeping in mind that its structure significantly affects how our device will behave. Let's move on. Another moving element of our multi-axis module is the Linmot linear rotary motor. The slider of this motor makes a movement consisting of a vertical linear motion and a rotational motion around the z-axis. This combination of these two movements can be performed as a joint motion of two coordinate systems. The first will move vertically, and we will rotate the second. Let's add the letter Z to the name of the third system. Since the slider moves together with the stator and the 1000 axis block, we will connect this system with the CS2X system as well. We will do it by using the drag and drop method again. Let's connect the last system in the same way to the third one. Due to the fact that this system is supposed to move in a rotational motion around the z-axis, we should add the letter Z and ROT to its name, indicating the rotation of this system. We have almost defined the kinematic chain of our device. The movement of the subsequent axis depends on the previous ones. This is indicated by its design and is reflected in the tree hierarchy. We will now proceed to setting the position of the coordinate systems. As you can see, every new system that we insert into the project appears at a point with 0, 0, 0 coordinates. This is why all our systems are at the beginning of the main coordinate system for now. It is important to note at this point that the starting position of the coordinate system moving in a straight line is irrelevant. However, if the system is to rotate in relation to any axis, then the position of the mentioned axis is important. This is due to the rules of geometric transformations. If you are willing to explore these principles, we suggest that you familiarize yourself with the principles of homogeneous transformation. Let's move the first system so that it is next to the block of the 500 module and has the same y and z coordinates as the end of our device's slider. In this case, we need to raise it by 125 mm up along the z-axis and 219 mm in the y-axis. This is due to the geometric dimensions of our device. All other systems move together with this system because they are connected to it. It's not clearly visible yet because all their axes overlap, but we will soon check back on it. The next system we will deal with is CS2X. Let's move it to the end of the slider. It is spaced by 1188 mm in the positive direction of the x-axis. Once again, we emphasize that the beginning location of these two coordinate systems is not important for the operation of our device, though it is recommended to maintain a certain order in the position of the beginnings of all systems related to the structure of our device. Let's move the CS3Z system to the end of the slider. Leave the CS4Z ROT system also at the end of the slider. Due to the dimensions of the linear motor, we have to move it down by 165 mm. We can move it a bit to confirm it's here. Let's turn it by a small degree. As we said before, the position of the center of the coordinate systems that move in a straight line is not relevant. To make our kinematic chain more visible, let's move the third system slightly up, for example by 65 mm. And leave the fourth system at the end of the slider. We can hide the solids for a moment. We now see the whole kinematic chain of our device. Black lines between the centers of the systems indicate connections between them. They also reflect the hierarchy in the tree. The coordinate systems with black lines form the same tree as the one on the left side of the screen, but only in 3 dimensions. By using the Options menu, we can display only a selected coordinate system or all systems from our project in the 3D space. Let's see what happens when we move the first of the coordinate systems. Let's rotate it around the y-axis, then z, and then x. Now we can clearly see that all systems are connected to it. Let's go back to our previous setting and restore the device's view. If all our coordinate systems are already in place, we can now attach to them the mechanical elements that make up our device. In Simultus, moving solids involves moving the coordinate systems to which they are connected. Therefore, if we want to move a solid, we must connect to it the selected coordinate system and move it. We connect solids with systems in the same way as we establish connections between systems. We simply drag the solid into the appropriate system using the drag and drop method. The body of the largest double 500 module will be stationary, so we don't have to connect it to any system. Linear module 1000 moves along the y-axis with the first system, so let's drag and drop it here. The stator with the block moves along the x-axis, so we will connect it to the next system. The slider moves with resultant motion, consisting of a vertical movement along the z-axis and a rotational movement. This is why we connect it to the last coordinate system. All moving mechanical elements are now connected to the appropriate coordinate systems. We'll perform a test by moving them around. By rotating the first system, we move the elements attached to it and to the systems that are connected to it. In the next part of the training, we will show how to control its movement along the y-axis. The next system will move in the x-axis, the third one in the z-axis, and the fourth will rotate around the z-axis. Let's create another coordinate system, which we will call base. By attaching all the other elements to it, including the 500 module, we will be able to fully position the device anywhere in our project space, as well as change its orientation without interfering with the relationships between its individual elements. At this point, it should be noted that Simultus can combine coordinate systems and 3D solids in 2 ways. The first is the one we have shown. We will show it again with the example of a slider. We will disconnect it again from the coordinate system. To disconnect the system, we drop it under the tree. Disconnected items are added to the list under the tree. They are not attached to any of the coordinate systems we created, but are currently attached to the main, global coordinate system of our project. The window on the right displays the local coordinates of the system or 3D solids relative to the system to which the element is attached. Let's check the coordinates of this element and notice that by connecting it to the coordinate system, its global position does not change. But for this to happen, the local coordinates had to be recalculated. Now we select the Move STL to New Layout option in the top menu. After the connection is made, the local coordinates of the system will now remain the same, and its global coordinates will change. In this case, the solid or coordinate system is moved to the new system without changing their local coordinates. However, their global position does change. The first way is set by default, but there are times when the second way is also useful. We invite you to the next part of the training, in which we will show you how to set our coordinate systems in motion, using the function blocks provided in the diagram.